Hello everyone, I'm Sahaj from Indiana University. I'm glad to present our work constructing compressed number lines of latent variables using a cognitive model of memory and deep neural networks. Recordings of neural activity from mammalian brains suggests representations that can give rise to mental number lines over different variables, including time, spatial distance, numerosity, integrated evidence, and pitch of tones. Many of these number lines are log compressed, providing a natural account for Weber-Fechner law observed in psychophysics. We developed a neural network that learns to construct log compressed number lines from a cognitive model of working memory, which can be described as a recurrent neural network with analytically derived weights. We combined deep learning with this working memory model and showed that the model learns to extract latent variables from the input and use them for modulation of recurrent weights, turning a timeline into a number line over relevant dimensions. We call this model the compressed number lines model. The working memory model contains two layers. In the first layer, we compute real domain Laplace transform using an array of log space decay constants, where the decay rate is modulated by the parameter alpha, which we learn using a neural network. In the second layer, we perform the inverse Laplace transform over the input of the first layer, which provides us with log compressed history of the past with respect to the current time step. In figure 1, we can see how the model of working memory performs in the absence of the modulation parameter alpha on the left. And on the right, we can see how reducing the value of alpha can reduce the decay rate and change the representation of the past. This is analogous to how velocity can modulate the time taken to cover a fixed amount of distance. In many cases, the variables that modulate the number of steps to an outcome are unknown. We use a fully connected neural network along with the working memory model to extract the variables of interest that modulate the number of steps to an outcome and predict the event using the architecture mentioned in figure 2. We tested our network on two event prediction experiments, where event A predicted event B such that the elapsed time between them depends on a latent variable, which can be learned as a combination of the input features. In the first experiment, the number of steps between A and B is modulated by a linear combination of two input signals. The models had to learn the relationship between the input signals to correctly predict the occurrence of event B. We conduct the experiment at 3 different scales, with examples of sequence length 200, 2000, and 20,000, where the number of steps between A and B in the absence of modulatory inputs were 50, 500, and 5,000 respectively. Here we can see that the errors increase proportionally to the scale. In this experiment, which is our second experiment, a pattern with 16 binary values is presented at each time step. The number of steps between A and B is modulated by the number of times a target pattern is repeated in a sequence of fixed length. In other words, B occurs following a fixed number of occurrences of the target pattern after we have seen A. We conducted the experiment at 2 different scales, one with 10 target counts in a 200 length sequence, and the other with 200 target counts in a 2000 length sequence. Overall, the proposed approach was able to represent latent variables in the form of compressed number lines, which simplified relationship learning and performed better than other models. Log compression of the number lines also gave rise to errors that were proportional to the magnitude of the latent variable, as commonly observed in human data, as characterized through Weber's law. Thank you for watching my video. Please feel free to reach out. I'd be happy to answer any questions or provide code for the experiments. Thanks again.